In this video, we're going to talk about section 9C, dealing with exponential modeling. And here we're going to investigate exponential functions and some of their many applications in mathematical models. Okay. We're going to start off with a short review of logarithms, because basically in this section, there's going to be logarithms involved here. Okay. Now, the basic properties of logarithms lead to two very useful algebraic techniques. These techniques apply to logarithms with any base, but we will focus on common logarithms, which are, of course, base 10. And back in section 8C, I believe, I think it was section 8C, it was in one of the videos. I take that back, it was 8B. 8B dealt with, I gave a short review of logarithms. You might want to check that video out as well if you're not familiar with logarithms, okay? We can solve for a variable that appears in an exponent by taking the logarithm on both sides of an equation, as long as both sides are positive, and applying the rule that log to the base 10 of a raised to the power of x, we can apply the power rule by pulling the exponent, which is your x, in front of the logarithm. So it will be equal to x times log to the base 10 of a. And then the second, we can solve for a variable that appears within a logarithm by making both sides of the equation into powers of 10. And then applying the rule that 10 raised to the log to the base 10 of x will be equal to x. And that's as long as x is greater than 0 or x is positive. Here, base 10 and log to the base 10 are inverses of each other. You'll be left with x. So like in this example, and we're going to do a few of these to start off with, and then we'll go into the topic of exponential functions here. This example, you're going to solve for x in the equation 2 to the power of x equal to 50. So the first thing we do here is take log to the base 10 on both sides of this equation, or we can just simply take the log on both sides, as you can see here. And then we apply the rule that log to the base 10 of a to some power of x, applying the power rule by pulling the x in front of log to the base 10. So we got x times log to the base 10 of 2 is equal to log to the base 10 of 50. We just took the log on both sides and pulled the exponent in front of log to the base 10 of 2. Now here we divide both sides by log to the base 10 of 2 to solve for x. You're going to get this, log to the base 10 of 50 divided by log to the base 10 of 2. Okay? Now they evaluated log to the base 10 of 50 in the calculator to get the numerator of 1.69897. And then evaluated log to the base 10 of 2 to get 0.30103. If we divide those two quantities together, you get approximately 5.644. That would be the value of x. Okay. Now this next example, here we're going to solve for x in the equation 2 times log to the base 10 of x equal to 15. Okay. Now we're going to get log to the base 10 of x by itself by dividing both sides of this equation by 2. We're going to get this. Log to the base 10 of x is equal to 15 divided by 2. And if you do 15 divided by 2, you're going to get 7.5. Okay. Now because your x is within that logarithmic expression, we're going to make both sides of the equation into powers of 10. So here we're going to have the base 10 on both sides of this equation. So it'll be 10 raised to the log to the base 10 of x, equaling to 10 raised to the 7.5 power. And then there is a rule that states if you have 10 raised to the log to the base 10 of x, that's going to be equal to x because 10 and log to the base 10 are inverses. You'll be left with x. And then that's equal to 10 to the 7.5 power. And that'll be equivalent to this answer in scientific notation, 3.1623 times 10 to the 7. So on the calculator, you'll do 10 and then the hat key 7.5. And now let's look at some examples of equations that are logarithms. Start with this one. Here we're going to solve for x. Here we've got 3 to the power of x equal to 81. Okay? Now, the way we're going to have to do that is, to solve this equation, we start by taking the logarithm on both sides. And we're going to take log to the base 10 on both sides. So here I'm taking the log to the base 10 on both sides of this equation. And then I'm going to apply the rule that says I can pull the exponent in front of the logarithm. We call that in college algebra the power rule. So when we pull the x out in front, it will be x times log to the base 10 of 3 equals log to the base 10 of 81. And now to solve for x, I'm multiplying by log to the base 10 of 3. So I need to divide both sides by log to the base 10 of 3. And this is where we use our calculator to do this. And in fact, we can type all of this in the graphing calculator. Okay. All right, in this case here, that numerator is log to the base 10 of 81. But your calculator does have the log key. That's understood to be log to the base 10. So we press the log key and then type in 81. Don't worry about the base 10 because it's understood to be log to the base 10 of 81. And we close the parentheses, divide by, and then press the log key again, and then 3, close parentheses, and then hit enter. That will give you the answer of 4. So here x equal 4 is what 3 to the power of x is equal to. Equal to 81. That's what x is equal to, which is what we're looking for. Okay. All right, the next example. Here we're going to solve for the following equation for the unknown quantity of x. In this case here, we've got 7 to the power of x equal to 40. 7 to the x equals 40. So we're going to do the same thing that we did in example 1. And that is to take log to the base 10 on both sides of the equation. So we're going to have log to the base 10 on this side and log to the base 10 on the other side. And then we're going to apply that rule where we can pull the exponent in front of the logarithm. We use a power rule here. So here, if I bring the x out in front, it will be x times log to the base 10 of 7 equals log to the base 10 of 40. And then we solve for x. That x is multiplied by log to the base 10 of 7, so we're going to divide both sides by log to the base 10 of 7. So this is what x will be equal to as an exact value. Now here we're going to round to 2 decimal places, which is to the nearest hundredth. So in this case, we're going to press the log key and then type in the number 40, close parentheses, divided by, press the log key, and then 7, close parentheses, and then hit enter. Now to the nearest hundredth, or to 2 decimal places, this 5 will increase to 89 to a 90, so it'll be 1.90. So x is approximately 1.90. Okay. Okay, another example like that would be 3 to the 2x equals 17. 3 to the 2x equals 17. Okay, we'll do the same thing by taking the log to the base 10 on both sides of this equation. And in this case, we bring the exponent out in front using the power rule here. So the 2x will be in front. That's going to be multiplied by log to the base 10 of 3 equaling to log to the base 10 of 17. Now here we're going to get the x by itself. It's being multiplied by 2 times log to the base 10 of 3. So I'm going to divide both sides by 2 log to the base 10 of 3. That means x is going to be by itself because the 2 and log to the base 10 of 3 are gone. Now this we can type in the calculator. I'll go ahead and rewrite that as the exact value. But here they want the approximate value to 2 decimal places. So here we'll do the log key and then 17, close parentheses, divided by, the denominator will be 2. Well, actually, what I'm going to do here is put that in parentheses to be on the safe side. So left parentheses, 2 log of 3. And then close the parentheses for your log, and then close it again. And then hit enter. To 2 decimal places, this will be approximately 1.29. So the approximate value of x will be 1.29. All right, let's say we have this example here. Log to the base 10 of x equals 3. Okay, now this is where that second case is, where you're going to have to write this as powers of 10. That means we're going to have the base of 10 on the left side and the base of 10 on the right side of this equation. So we're going to write this with powers of 10. So this will be 10 raised to this expression, log to the base 10 of x, equal 10 to that number, 3. Okay, so I'm putting powers of 10 on both sides of this equation. Because on the left side, if I have 10 raised to the log to the base 10 of whatever, it's going to be whatever. Because 10 and log to the base 10 are inverses. This will be gone, you'll be left with x equal to 10 to the third. And if you evaluate 10 to the third on your calculator, you'll get 1,000. So x will be equal to 1,000. And that's all there is to it. Okay, this next example, here we got log to the base 10 of x equal to 2.3. Okay, so I'm gonna write powers of 10 on both sides of this equation. Okay, this will be the exponent for the power of 10 on the left side. So I have 10 to the log to the base 10 of x equaling to 10 to the 2.3. Okay, so I'm putting powers of 10 on both sides of this equation. And then 10 to the log to the base 10 of x, just like in that last example, will be x because 10 and log to the base 10 are inverses of each other. So you'll have your x equal to 10 to the 2.3. And they want this to 2 decimal places. So this will be, in this case, type in 10, press the hash key for your exponent, and then 2.3, and enter. This will be approximately 199.53. 199.53. That's what the value of x is, or the approximate value of x. Okay. All right, here's another example. 7 times log to the base 10 of x equals to 3.8. 7 log to the base 10 of x equals 3.8. Now I'm first going to get log to the base 10 by itself. I'm multiplying it by 7, so I'm going to divide both sides by 7. So I have log to the base 10 of x, and I'm going to leave this as 3.8 divided by 7. Okay. Because I know if I do 3.8 divided by 7 on the calculator, I'm going to get a long decimal. So I'll leave this off, and I'll leave this as is until the end. And now we can put powers of 10 on both sides of this equation here. So this 10 will be 2 raised to the log to the base 10 of x, equaling to 10 will be raised to the 3.8 divided by 7. That 3.8 divided by 7, that will be your exponent for 10. And then if I have 10 raised to the log to the base 10 of whatever is whatever. So 10 to the log to the base 10 of x is x. And now to get the approximate value here, we type in 10, and then the hash key, and then I'm going to do 3.8 divided by 7 in that exponent, and then hit enter. And to 2 decimal places, this will be approximately 3.49. So the approximate value of x will be 3.49. Okay. All right, now let's look at one more of these logarithmic equations here, like this one. Log to the base 10 of 6 plus x in parentheses equals 4.2. Okay. Now, we got log to the base 10. What I'm going to do here is raise both sides of this equation. Well, actually, put powers of 10 on both sides of this equation. So I'm going to have a power of 10 raised to that expression right there, log to the base 10 of 6 plus x equal 10 raised to that number, 4.2. Now in this case, 10 to the log to the base 10 of whatever is whatever. So 10 raised to the log to the base 10 of 6 plus x is 6 plus x. And that's going to be equal to 10 raised to the 4.2. I'm not going to evaluate that until the end. Now, I want to get x by itself. I'm adding 6, so I need to subtract 6 on both sides. So here I'm going to have x is equal to 10 to the 4.2 and then minus 6. Now they want the approximate value to 2 decimal places here. So we're going to do 10 and then the hat key, 4.2. Now we need to get out of the exponential part, so we need to use our right arrow key to get out of that, and then minus 6. Now the 2 decimal places, this will be 15,842.93. That will be your approximate value of x. Okay, so that's just a review of some logarithms here. Now we did have a short review in video 8b. You might want to check on that video as well. Now let's talk about exponential functions here. An exponential function grows or decays by the same relative amount per unit time for any quantity q growing exponentially with a fractional growth rate r. This will be your formula. Q is equal to q sub 0 times 1 plus r. That quantity is to the power of t. Now q is going to be the value of the exponentially growing quantity at time t. Q sub 0 is the initial value of the quantity at t equals 0. R is equal to the fractional growth rate for the quantity. T is equal to time. Now negative values of R correspond to exponential decay. And note that the units of time used for T and R has to be the same. Okay? That's very important, because if it's not, then you have to convert it from one unit to another to get those units the same. That means if the time is in minutes, the R, the fractional growth rate, has to be in minutes as well. While an exponential growing quantity has a constant relative growth rate, its absolute growth rate increases. All right, so now let's look at a few examples of this. Let's say a privately owned forest that had 1 million acres of old growth is being cut at a rate of 6% per year. And in part A, we want to create an exponential function of the form q is equal to q sub 0 times the quantity 1 plus r to the t, where r is greater than 0 for the growth, r is less than 0 for decay, to model the situation described. Now, here it's being clear cut at a rate of 6% per year. That would mean, in this case, your fractional growth rate, or R, has to be, now 6%, it has to be negative, by the way. 6% as a decimal, you take 6, divide that by 100, on your calculator you'll get 0.06. So your R is going to be negative 0.06. And the form here is q is equal to q sub 0 times the quantity 1 plus r raised to the t. And it had 1,000,000 acres, so that means your Q sub 0 is 1,000,000. Q sub 0 is 1,000,000. So here, if we substitute that, we're going to have the Q equal to Q sub 0 is 1,000,000 times 1 plus negative, well, R is negative 0.06, so 1 plus negative 0.06, that's going to be raised to the t. And 1 plus a negative 0.06 will be 0.94. So you're going to have Q equals to 1,000,000 times 0.94 raised to the t. That would be the exponential function for this situation. So here you'll enter the 1,000,000, which is your Q sub 0, and this part right here will be that 0.94 raised to the t. So that's part A. Now in part B, you're going to create a table showing the value of the quantity Q for the first 10 years of growth. So here, use year sub 0 as 0 for the first year. Well, 0, that's 1,000,000. Now, for year 1, here we can do this in the calculator. And I'm going to show you the quick way of doing this. That way you won't have to enter that formula again. Let me clear this out. All right, I'm going to type in the 1,000,000 and then times 0.94 and then the hat key for your exponent. So for the first year, we'll type in the exponent of 1 and then hit enter. Now here they're telling you to round to the nearest whole number, so this will be 940,000 after the first year. Now for year 2, I'm going to show you how to do this the quick way. If you press the second key and enter at the bottom of your calculator, you'll get this back. And then I'm going to use my left arrow key to go up to that exponent and change that 1 to a 2. And then hit enter. So for year 2, it will be 883,600. And then for year 3, again, I'm going to do second enter, because the only thing that's going to change is your time. The Q sub 0 and the number in the parentheses remains the same. So I'm going to use my left arrow key to change that 2 to a 3. You'll see you get 830,584. And then for year 4, again, second enter. Use your left arrow key to change that 3 to a 4. Now we're going to round this up to the nearest whole number. That's going to be 780,749. And then for year 5, hit second and enter. Change your exponent from a 4 to a 5, and then hit enter. To the nearest whole number, that would be 733,904. And then for year 6, let's see, year 6, we do second enter, and then change that 5 to a 6 using your left arrow key, and then hit enter. This will be 689,870 if we round to the nearest whole number. $689,870. And then for year 7, Change this to a 7. You get 648,478 to the nearest whole number. So 648,478. And then for year number 8. So you pretty much get the idea of what I'm doing here. This will be 609,569 to the nearest whole number. And then year 9. Change that to a 9. That will be 572,995. And finally, year 10, second and enter. Change that 9 to a 10 in that exponent. We'll get 538,615. Now, as you can see here, the number of acres is decreasing year by year using that exponential function here. And now we're going to make a graph of the exponential function, and we're going to choose the one that would best fit this particular table. We can see that it is decreasing, so we know that D has to be eliminated. Also, I know B would not work because at B, for 0, it's starting off at less than 1 million. It's not starting off at 1 million for year 0. So B is out. Okay, now we have to choose either A or C. Now in the homework, you're probably going to have to use that magnifying glass icon, click on that to blow up that particular graph to see if it's going to fit this particular table. Okay, so here I'm thinking it's going to be A. Yeah, it'll have to be A. Because I don't think when it's declining, it's not declining as steep as the one in C. Because at C, for 10 years, it's somewhere around 300,000. We haven't reached that amount yet. So it's got to be A. Okay, here's another example. Consider the following case of exponential growth. Complete parts A through C below. Your starting salary at a new job is $1,800 per month, and you get annual raises of 4% per year. Okay, so we know that it's going to be increasing, that our fractional growth rate will be positive. Okay, and we want to create an exponential function of the form q equal q sub 0 times 1 plus r quantity to the t power. Well, here that q sub 0 is 1,800. And in this case, here, your fractional growth rate, you're getting annual raises of 4% per year. So your R is going to be 0.04. Again, take the 4 divided that by 100 when you convert a percent to a decimal. Okay, so formula Q equal Q sub 0 times the quantity 1 plus R raised to the T make that a ton sign. So Q is equal to Q, that's Q sub 0 is 1,800 times 1 plus R, that's going to be 0.04, raised to the t power. And 1 plus 0.04 will be 1.04. So we got q is equal to 1800 times 1.04 raised to the t. So here your 1800 goes here, and the 1.04 goes where the exponent of t is. Okay. That will be your exponential function for this monthly salary situation. And now we're going to create the table showing the value of the quantity Q for the first 10 years of growth. So we're going to do the same thing as we did in that last example. Okay, year 0 is 1800. Year 1, we're going to do this 1800 times 1.04, press the hash key for your exponent, and type in the exponent for that year, which will be 1, and then hit enter. And again, and here we're going to round to 2 decimal places because that's what the direction says here. So this will be $1,872. And you'll type that in as 1872 with 2 zeros behind the decimal point. And then for year 2, if you recall, you do second and enter at the bottom of your calculator to bring this up, and then you change your exponent using your left arrow key to a 2, and then hit enter. So this will be $1,946.88 for year 2. And then for year 3, second enter, change this to a 3, and this will be $2,024.76, rounded to 2 decimal places. And then year 4, second enter, change that 3 to a 4, using your left arrow key, be $2,105.75, $2,105.75. And then year 5, again, second enter, hit your left arrow key, change that to a 5. This will be $2,189.98 to 2 decimal places. And then for year 6, second enter, and we change the 5 to a 6. This will be $2,277.57. $22.77 and 57 for year 6. And then for year 7, second enter, and then change that 6 to a 7. This will be $2,368.68. And then year 8, second enter, left arrow, change that 7 to an 8. So year 8, $2,463.42 after year 8. And then year 9, so we'll do second enter again, change the 8 to a 9. This will be $2,561.96. And then finally year 10. Change that 8 to a 10. A 9 to a 10. So it'll be $2,664.44. Okay. So that's our table right there for this particular situation for the first 10 years. And then we're going to make a graph of the exponential function and choose the one that will best fit. This one. We can see that these salary values per month is on the increase, so I can eliminate D because you can see that graph is decreasing. Okay. C would not work as well because at 10 years, it's somewhere between 1,200 and 1,800. At 10, we're at 2,664, so we can eliminate C. So we got A and B to choose from. This graph only goes up to year 9, so we can eliminate A, so it had to be B. That would be the best one for that particular situation. So again, you'll have to kind of use the magnifying glass icon to blow up those graphs to see which one would best fit that particular situation. Okay. Now the forms of the exponential function. If the given growth or decay rate, if given the growth or decay rate R, then you're going to use that form. Q equal Q sub 0 times the quantity 1 plus R raised to the T, which is what we did. And keep in mind that R is positive for growth and negative for decay. If you're given the doubling time, which is T sub double, you're going to use the form Q is equal to Q sub 0 times 2 raised to the T divided by T sub double. And if given the half-life, which is T sub half, you're going to use the form Q equal to Q sub 0 times 1/2 raised to the power of T divided by T sub half. Okay. Now these last two we've done in one of the other videos in chapter 8, I believe. Yeah. Okay, let's look at example 10. If the price of gold increases at a monthly rate of 1.9%, by what percentage does it decrease in a year? Okay, so let's start off by using that Q equal to Q sub 0 times the quantity 1 plus R raised to the T. Well, it's decreasing at a monthly rate of 1.9%. That means our R has to be a negative value. And then 1.9% as a decimal, 1.9 divided by 100 would be 0.019. If it's decreasing by a monthly rate, that means T, if it's in a year, how many months are there in a year? Has to be 12. Okay? Because keep in mind the R and the T, those values have to be consistent. If it's a monthly rate of negative 0.019, then the time has to be in months as well. So T has to be 12. Okay? Now if I do Q equaling to Q sub 0 times 1 plus R, which is negative 0.019, raised to the 12th. Now if I do 1 plus a negative 0.019, I'm going to get 0.981. And that's going to be to the 12th power. And if I do 0.981 raised to the 12th, I will get 0.981. Sorry. It's 0.794 if I round that off to 3 decimal places. So this will be Q equal to Q sub 0 times 0.794. Now here I'm going to use that particular value of 0.794, that factor, okay? Because this is what's going to help me find the annual inflation rate, okay? Now in this case here, there is a formula that says here if you have 1 plus the annual inflation rate, that's going to be equal to whatever this factor is right here. In this case, it's equal to 0.794. So to find the annual inflation rate, I'm adding 1, so I need to subtract 1 on both sides. So my annual inflation rate I have to do 0.794 minus 1 to get negative 0.206. Now, that's a decimal. But as a percent, we have to take that negative 0.206 and multiply it by 100. Negative 0.206 multiplied by 100, that would be negative 20.6. And that's going to be as a percent. So the annual inflation rate there will be negative 20.6%. Okay. And finally, example 11. Now I'm going to modify example 11 a bit, and I've already modified that in the homework as well, okay? Do not worry about D, part D. We're only going to complete parts A through C. And it says here, annual oil production for a region was about 500 million tons in 1950. Production increased at a rate of 7.3% per year between 1950 and 1973. But the rate of growth then slowed. The oil production reached approximately 4.1 billion tons per year in 2016. We're going to complete parts A through C. Don't worry about D. I've already modified that in the homework. In part A, using the growth rate of 7.3% for the period 1950 to 1973, approximately what was the oil production in 1973? Okay, now I'm going to have to do this at the very bottom of this sheet. Okay, we have to find out what the time is from 1950 to 1973. That's this right here. So if I subtract 1973 minus 1950, that will give me 23. And here Q sub 0, it was about 500 million tons. Now here, I'm just going to use the number 500. So my Q sub 0 is going to be 500. And the R, the projection increased at a rate of 7.3% per year. That will mean R is going to be 7.3%, or as a decimal, 0.073. And it is positive because the projection increased. So R has to be positive. So here we're going to use this formula here. Q is equal to Q sub 0 times the quantity 1 plus R raised to the T. And then we'll just start substituting here. Q sub 0 was 500 multiplied by 1 plus R, that's 0.073, that's raised to the T. That's going to be 23. Now 1 plus 0.073 will be 1.073, so I got 500 times 1.073 to the 23rd. Now, if I type all that in the calculator, that'd be 500 times 1.073, then the hat key for the exponent, 23, and then hit enter. This will be, in this case, 27.9 million, because the 500 there represents 500 million. But here they want the answer in billion, okay? If I move this decimal point 3 places to the left, it will be in billion, because that number represents the millions. Move this decimal point 1, 2, 3 places to the left, it'll be between the 2 and the 5, and it will be in billion. So this will be I'm going to say approximately 2.5 billion. So here, to answer part A, the oil production is approximately 2.5 billion tons in 1973. Okay, that's how we solve that particular problem here. Okay, now part B. It says here, starting from the result in part A, approximately how much oil would have been produced in 2016 if growth in production had continued at a rate of 7.3% between 1973 and 2016. Compare this result to the actual 2016 figure given above. Okay. So now we need to find out what the time is going to be. Your T is going to be from 1973 to 2016. So if I do 2016 minus 1973, that will give me 43 years. The R is going to still be 0.073 because that rate's still going to be the same. Your Q sub 0 this time is 2.5 billion. Here I'm using what I came up with in part A. That's going to be Q sub 0. So I got Q equal to Q sub 0 times 1 plus R raised to the T. So Q is equal to Q sub 0, that's 2.5, multiplied by 1 plus R, which is 0.073, raised to the T, that's 43. And of course, if I add 1 plus 0.073, I'm going to have 1.073. And this I can enter in the calculator. So this will be 2.5 times 1.073, then the hat key, and then 43. And I'm going to say to one decimal place, 51.7 billion. $51.7 billion. That will be the oil production in billion tons for 2016. Now they ask us to compare that result to the actual 2016 figure. Okay, in 2016, I need to bring this down. The oil production was 4.1 billion tons per year in 2016. Now you can see here that actual figure is, and here they give you the choice here in your drop down menu. It's going to be far less than. Far less than the figure calculated using the 7.3% growth rate. Okay. And part C, starting from the result in part A, approximately how much oil would have been produced in 2016 if growth in production had proceeded at the rate of 2.6 between 1973 and 2016. Okay. And then compare that result to the actual 2016 figure given above. So I'm going to do part C over here. Okay. In this case here, your Q sub 0, that's going to be that 2.5 billion that we came up with in part A. Your R is 2.6% this time. Okay? Because in that problem here, if the growth in production had proceeded at the rate of 2.6 between 73 and 2016, so 2.6% as a decimal will be 0.026. Your T is still going to be from 2016 and all the way down to 1973. That difference is still 43. So here we got Q equal to Q sub 0 times 1 plus R, the quantities to the power of T. So Q is equal to Q sub 0, that's 2.5, times 1 plus R, which is 0.026, raised to the power of T, that's 43. And 1 plus 0.026 will be 1.026, so I got Q is equal to 2.5 times 1.026 to the 43rd. And we can type that in the calculator as well. So we got 2.5 times 1.026, the hat key, and then 43. To one decimal place, we came up with 7.5. And that's in billion. So the oil production is approximately 7.5 billion tons in 2016. Now we can compare that to the 4.1 billion back in the year 2016. If you were to compare that based on that formula, that actual figure will be, again, far less than. Compare the actual figure of 4.1 billion to this 7.5 from that formula, you'll see that it's far less than the figure calculated using the 2.6% growth rate. Okay, don't worry about part D. I eliminated that in the homework, and I'm eliminating that in this video. Okay, so that will conclude this video on exponential modeling.